June 15th, 1943. Naval Air Technical Arsenal, Yokosuka, Japan. Lieutenant Commander Minoru Genda stood on the tarmac, staring at an aircraft that represented everything Japanese naval aviation feared was coming. The Grumman F6F Hellcat sat under armed guard, its dark blue paint still showing traces of salt spray from the Pacific. American white stars had been hastily painted over with Japanese Hinomaru roundels, but the deception fooled no one who saw this massive fighter up close. Genda had been one of the principal tactical planners for the Pearl Harbor attack. He understood better than most how the war in the air had shifted since that December morning 18 months earlier. Japanese pilots still flew Zeros, the same basic airframe that had dominated the skies in 1941 and early 1942. But the Americans had clearly moved forward. This captured Hellcat represented the future, and Genda had been ordered to discover exactly what kind of future Japanese naval aviation faced. The aircraft had been captured intact 3 weeks earlier on June 22, 1943, during the fighting over the Russell Islands. Ensign James Maguire had been escorting a strike mission when his engine suffered catastrophic mechanical failure. Oil pressure dropped to zero. Cylinder head temperatures soared beyond redline. He had no choice but to ditch. Maguire managed a controlled water landing in a lagoon on Bonica Island, which Japanese forces still partially controlled. He inflated his life raft and began paddling toward what he thought was American-held territory. He paddled in the wrong direction. Japanese troops captured Maguire within 2 hours. The Hellcat floated in shallow water, virtually undamaged except for saltwater intrusion into the engine compartment. Within 6 hours, Japanese engineers had attached flotation devices to the wings and towed the aircraft to a transport ship. Within 5 days, it reached Yokosuka, where the Imperial Japanese Navy's most experienced test pilots and engineers waited to examine America's newest carrier fighter. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Hellcat represented a quantum leap from the Wildcat that Japanese pilots had grown accustomed to facing. Imperial Japanese Navy intelligence had been tracking reports of this new fighter since its combat debut in late August 1942 during the Guadalcanal campaign. Initial engagement reports from Japanese pilots had been alarming. The new American fighter was faster than the Zero. It was more heavily armed than the Zero. It could absorb tremendous battle damage and continue fighting. It could outdive any Japanese aircraft. Pilots reported that it seemed purpose-built to counter every advantage the Zero possessed. But reports from combat, filtered through adrenaline and fear and confusion, were notoriously unreliable. Japanese intelligence officers had spent months trying to separate fact from exaggeration in pilot debriefings. Some claimed the Hellcat could reach speeds of 400 miles per hour. Others insisted it carried 8 machine guns instead of 6. Still others reported armor so thick that 20mm cannon shells bounced off harmlessly. Which claims were real? Which were products of stressed minds in desperate combat? The captured aircraft would finally provide definitive answers. Commander Tadashi Nakajima led the technical evaluation team. He had designed several Japanese aircraft types and understood airframe engineering at the deepest level. His team spent the first week carefully documenting every aspect of the Hellcat's construction before attempting any restoration work. They measured, photographed, sketched, and analyzed with meticulous precision. What they discovered during that initial examination shocked them profoundly. The first revelation came when engineers measured the aluminum skin thickness on the fuselage and wings. 0.050 inches, nearly 60% thicker than the Zero's 0.032-inch skin. The difference seemed small on paper, but the implications were enormous. One engineer demonstrated by striking both aircraft with the same hammer using identical force. The Zero's skin dented visibly. The Hellcat's skin showed barely a mark. In combat, this translated directly to survivability. Bullets that would tear through a Zero's thin skin might not even penetrate the Hellcat's structure. The armor protection stunned the Japanese engineers even more than the skin thickness. Behind the pilot's seat, Thick steel plates measuring 8 mm covered the entire back of the cockpit. Additional armor protected the pilot's head. Armored glass, 3/4 of an inch thick and laminated with multiple layers, protected the windscreen. The oil cooler had steel shields. The engine had protective baffles. Even the ammunition boxes were armored to prevent cook-offs from enemy fire. Nakajima's team calculated the total weight of armor protection, 412 pounds. The Hellcat carried more protective armor than some Japanese aircraft weighed empty. The Zero, by comparison, carried 0 pounds of pilot armor in early models. Later variants added minimal head armor that offered protection against small arms fire, but nothing more. The philosophical difference was stark and undeniable. American designers had decided pilot survival was worth the weight penalty. Japanese designers had decided pilot survival was less important than performance. The self-sealing fuel tanks represented another technological gap that dismayed the evaluation team. The Hellcat's fuel tanks incorporated multiple layers of rubber compounds that would automatically seal bullet holes through chemical reactions triggered by fuel contact. A tank could take multiple hits and lose only minimal fuel before the sealant plugged the holes. Japanese engineers examined the tank construction with growing frustration. They understood the principle, they knew the chemistry, but Japanese industry lacked the synthetic rubber production capacity to manufacture such tanks in the quantities needed for widespread use. Every major industrial nation except Japan had developed self-sealing tank technology by 1943. Britain had perfected the technology in 1939. America had deployed it across all combat aircraft by 1941. Germany had implemented it by 1942. Even Italy had crude self-sealing systems. Japan alone, among major combatants, still flew fighters with unprotected aluminum fuel tanks that ignited instantly when hit by incendiary ammunition. The resource constraints and industrial limitations that would ultimately doom Japan's war effort were already visible in this single technological deficiency. The engine compartment provided the next revelation. The Pratt & Whitney R2800 double-wasp radial engine displaced 2,800 cubic inches and produced 2,000 horsepower at war emergency power settings, more than twice the horsepower of the Nakajima Sakai engine in the Zero. The engine alone weighed 2,400 pounds, nearly half the Zero's empty weight, but that enormous power enabled performance that Japanese engines simply couldn't match. The supercharger system used 2 stages of compression with intercooling between stages. This allowed the engine to maintain high power output at altitudes where Japanese engines were gasping for air. The fuel injection system precisely metered gasoline under all flight conditions, eliminating the carburetor problems that plagued the Zero during negative G maneuvers. The engine could run inverted, could handle violent aerobatics, could operate continuously at full power for extended periods without overheating. Japanese engineers stripped the engine down to individual components over 5 days of careful disassembly. They measured tolerances, analyzed metallurgy, documented manufacturing techniques. The precision was extraordinary, but not beyond Japanese capability. The materials, however, revealed the gap. The Americans were using alloy steels and heat treatments that Japanese industry struggled to replicate consistently. The aluminum alloys showed compositions that Japanese metallurgists had only achieved in laboratory settings, never in production quantities. The armament installation demonstrated another American advantage. 6 Browning M250 caliber machine guns, 3 in each wing panel, with 400 rounds per gun. Total ammunition load 2,400 rounds. The Zero carried 2 7.7mm machine guns with 500 rounds each, and 2 20mm cannon with 60 rounds each. Total projectile count 1,120 rounds. The Hellcat carried more than twice as many rounds and could fire for nearly 30 seconds continuously. The Zero's cannon ammunition exhausted after 12 seconds of firing. But the real difference wasn't in the quantity of ammunition. It was in the effectiveness of the 50 caliber projectile. The Browning M2 fired a heavy bullet at high velocity that could penetrate armor, ignite fuel tanks, and destroy structure. The combination of 6 guns firing simultaneously created a cone of destruction that shredded targets. Japanese pilots who survived encounters with Hellcats consistently reported that even brief bursts caused catastrophic damage. A 1-second burst put approximately 60-50 caliber rounds into the target area. Against a Zero's thin skin and unprotected fuel tanks, this was absolutely devastating. The hydraulic systems showed American engineering philosophy clearly. Hydraulic pressure operated the landing gear, flaps, dive brakes, cowl flaps, wing fold mechanism, and arresting hook. Everything was powered, everything was efficient, everything reduced pilot workload. The Zero required manual operation for most systems. Pilots had to pump landing gear up and down by hand using a mechanical lever. Flaps required manual cranking. Every system demanded physical effort that tired pilots during long missions. After 7 days of static examination and documentation, the restoration work began. Salt water had flooded the engine compartment during ditching and subsequent recovery. The engine required complete disassembly, cleaning, and rebuilding. Japanese mechanics worked with captured spare parts and carefully fabricated replacements where necessary. The propeller had been damaged during the water landing and required replacement. No suitable Japanese propeller existed, so engineers modified a propeller from a captured P-38 Lightning to approximate the correct diameter and pitch. The electrical system needed rewiring throughout. The radio equipment, though intact, used American frequencies and encryption systems that Japanese forces couldn't utilize. The instrument panel showed some water damage requiring repair, but structurally, the airframe was sound. The fuselage showed no cracks or deformation. The wings were intact. The control surfaces operated smoothly. The tail section was undamaged. 3 weeks after the Hellcat's arrival at Yokosuka, on July 6, 1943, the restoration was complete. The aircraft had been repainted in standard Japanese Navy colors to prevent any identification confusion during test flights. Fresh Hinomaru roundels marked the fuselage and wings. Japanese characters identified it as a captured enemy aircraft under test. Armed guards maintained constant watch, preventing unauthorized access and ensuring no sensitive information leaked beyond cleared personnel. Lieutenant Commander Genda, despite his staff responsibilities and high rank, insisted on making the first evaluation flight himself. His experience was unmatched. He had flown Zeros since the type's earliest deployment. He understood fighter combat at the highest level, both theoretically and practically. He knew what questions needed answering, and he knew that understanding the enemy's capabilities might mean the difference between survival and extinction for Japanese naval aviation. The morning of July 6th dawned clear over Tokyo Bay. Genda arrived at the flight line before sunrise, conducting his pre-flight inspection by flashlight and early morning twilight. The Hellcat looked massive compared to a Zero. It looked brutish and industrial rather than elegant, but as Genda walked around the aircraft, checking control surfaces and examining the structure, he began to appreciate the design philosophy. This was not an aircraft built to impress observers with graceful lines. This was an aircraft built to win battles through overwhelming capability. He climbed into the cockpit using footholds built into the fuselage. The cockpit was spacious compared to the Zero's cramped quarters. He could move freely. Instruments were logically arranged and clearly marked. The control stick fell naturally to hand. The throttle on the left side was positioned perfectly. The rudder pedals adjusted for pilot leg length. Everything about the ergonomics suggested that American designers understood pilot comfort mattered for combat effectiveness during long missions. Genda started the enormous Pratt & Whitney engine using the electric starter. The 2,400-pound radial caught immediately and settled into a powerful, steady rumble that shook the entire airframe. The sound was deeper and louder than any Japanese engine, a bass thunder that spoke of enormous displacement and prodigious power. He carefully advanced the throttle, watching oil pressure rise into the green, monitoring cylinder head temperatures, verifying fuel flow. Everything operated exactly as documented in the captured technical manual that Japanese translators had been working through. After the engine reached operating temperature, Genda signaled ground crew and began taxiing toward the runway. The tailwheel steering felt different from the Zero, heavier and more deliberate. The massive engine and heavy propeller ahead of the cockpit required the typical fighter pilot weaving to see forward around the long nose. But visibility was generally good, and the aircraft handled predictably on the ground. At the runway threshold, Genda completed final checks and scanned the circuit for traffic. The control tower, staffed by officers cleared for this classified test program, gave clearance for takeoff. Genda advanced the throttle smoothly to full power and released the brakes. The acceleration was extraordinary. The massive engine developed thrust that pushed him back into the seat with authority. The Hellcat surged forward, gathering speed rapidly. At 78 knots indicated, Genda pulled back gently on the stick. Hellcat leaped into the air, climbing away from the runway with power that seemed impossible for a single-engine fighter. The initial climb rate shocked him immediately. At military power, not even the maximum war emergency power available, the Hellcat climbed at over 3,000 feet per minute. The Zero, even with a light fuel load and reduced ammunition, could manage perhaps 2,500 feet per minute under ideal conditions. In combat configuration with full fuel and weapons, the Zero's climb rate dropped to perhaps 1,500 feet per minute. The Hellcat, fully loaded with fuel, ammunition, and armor, was outclimbing the Zero by a massive margin. At 3,000 feet, Genda leveled off and began exploring the flight characteristics systematically. The controls felt heavier than the Zero's feather-light touch, but not excessively so. The aircraft responded crisply to inputs. Roll rate was impressive for such a large, heavy fighter. Pitch response was quick and predictable. The Hellcat felt stable and solid, inspiring confidence rather than demanding constant attention. Genda began methodically pushing the speed envelope. He advanced the throttle further, watching the airspeed indicator climb. 200 knots, 220, 240, 260. The controls remained responsive and effective at speeds where the Zero's ailerons would be nearly frozen from aerodynamic forces. At 280 knots, approximately 320 miles per hour, the Hellcat still handled beautifully. The ailerons were firm but perfectly usable. The aircraft rolled predictably and quickly. He climbed to 10,000 feet and began combat maneuvers, hard turns to explore turn radius and rate. The Hellcat couldn't match the Zero's legendary turning ability at low speeds. That was expected. The wing loading was simply too high. The Hellcat weighed nearly 13,000 pounds fully loaded compared to the Zero's 5,500 pounds. But what surprised Genda was how well the Hellcat could sustain turns at high speed. Where the Zero's light structure limited G-forces to prevent wing failure, the Hellcat's robust construction allowed aggressive maneuvering at speeds above 250 knots. He tried negative G maneuvers, the type that killed Zero engines instantly by starving the float carburetors. He pushed the stick forward firmly, floating against his harness straps. The engine continued running smoothly without hesitation. Fuel injection maintained perfect mixture under all attitudes. He tried rolling inverted and pulling through. The engine never missed a beat. The implications for combat tactics were profound. American pilots could escape pursuit through violent maneuvers that Japanese pilots simply couldn't follow without their engines dying. Genda tested high-speed dives, pushing the Hellcat to speeds approaching 400 miles per hour. The airframe remained solid and controllable. No flutter, no vibration, no structural concerns. The dive brakes, when deployed, gave excellent speed control without adverse buffeting. He tested the stall characteristics at various configurations and found them benign and predictable. The aircraft gave plenty of warning before stall through buffet and control mushiness. Recovery was straightforward and immediate. After 40 minutes of intensive flight testing, Genda had learned what he needed to know. He established a landing pattern and brought the Hellcat back to the runway. The approach speed was higher than the Zero's, but the aircraft remained stable and controllable. He touched down smoothly and rolled out, then taxied back to the secure hangar area where the technical team waited eagerly for his report. Genda climbed down from the cockpit with a grim expression. Commander Nakajima approached immediately, reading the concern on his face. The two men walked toward the debriefing room in silence, while guards secured the aircraft. Inside the room, with the door closed and only cleared personnel present, Genda began his verbal report, while his hands still trembled slightly from adrenaline. The F6F outperforms the Zero in all aspects except low-speed maneuverability, he stated flatly, using words that would later appear in official reports and shock the Naval General Staff. It climbs faster, it dives faster, it flies faster in level flight, it can sustain higher speeds in combat maneuvers. The engine never falters under -G. The controls remain effective at speeds where our aircraft become uncontrollable. The armor protection would allow the pilot to survive hits that would kill our pilots instantly. The firepower from 6 heavy machine guns would destroy our aircraft with any sustained burst. He paused, organizing his thoughts, then continued with the assessment that would ultimately reach Admiral Yamamoto himself. The Americans have built a fighter specifically designed to counter the Zero. Every advantage we possessed in 1941 and early 1942 has been systematically eliminated. They accepted weight penalties for protection and power, then overcame those penalties with brute force engineering. The Hellcat is not elegant, it is not refined, but it is devastatingly effective. Nakajima asked the critical question that everyone in the room was thinking. Can we match its performance with modifications to the Zero? Genda's response was immediate and definitive. No, the fundamental design philosophy is different. The Zero achieves performance through lightness and optimization. The Hellcat achieves performance through power and protection. To match the Hellcat, we would need to add armor, which adds weight. We would need to add self-sealing fuel tanks, which adds more weight. We would need a more powerful engine, which adds even more weight. By the time we finished, we would have a different aircraft entirely, and we don't have engines powerful enough to maintain performance with all that added weight. The silence in the room was profound. Every engineer and officer present understood the implications. Japanese naval aviation had reached a technological dead end. The Zero had been optimized to its absolute limit. Further development could only add incremental improvements. Meanwhile, American industry had leapfrogged an entire generation ahead with fighters purpose-built for the kind of air combat that modern warfare demanded. Over the following 3 weeks, additional test pilots flew the captured Hellcat. Each flight confirmed and expanded Genda's initial assessment. Lieutenant Saburo Sakai, one of Japan's highest-scoring aces with combat experience against every American fighter type, flew extensive mock combat trials against Zeros. The results were devastating for Japanese morale. In simulated combat at altitudes above 15,000 feet, where most engagements occurred, the Hellcat dominated absolutely. The Zero pilot could turn inside the Hellcat at speeds below 200 knots, but the Hellcat pilot could simply extend away using superior speed. The Zero couldn't catch it in level flight. The Zero couldn't follow it in dives. The Zero couldn't maintain energy in sustained combat. Within minutes, the Hellcat held every advantage of position, altitude, and energy state. Sakai's report was brutally honest. Against an informed Hellcat pilot who understands energy tactics, the Zero cannot win. We can only survive by avoiding combat or by achieving perfect surprise. In any sustained engagement where both pilots see each other, the Hellcat will dictate the terms of combat and eventually destroy us. The technical analysis conducted over the following weeks revealed layer after layer of American advantages that Japanese industry simply couldn't replicate. The metallurgical examination of the Hellcat structure proved particularly discouraging. Samples of the aluminum alloys were sent to the Imperial Japanese Navy's Metallurgical Laboratory for detailed analysis. The results confirmed what engineers had suspected. The Americans were using aluminum alloys with superior strength-to-weight ratios that Japanese industry had only achieved in small laboratory batches, never in the massive production quantities required for aircraft manufacturing. The alloy designated by the Americans as 7075, an aluminum-zinc-magnesium-copper alloy, showed properties that exceeded anything in widespread Japanese production. It was stronger than standard duralumin, more fatigue-resistant under repeated stress cycles, and could be formed and welded using existing manufacturing techniques. But it required raw materials that Japan's shrinking resource base couldn't provide in sufficient quantities. The zinc alone posed problems. Japan's domestic zinc production was barely adequate for existing needs. Diverting zinc to aircraft alloy production would mean shortages elsewhere in the war economy. The magnesium content presented even greater challenges. Japan imported most of its magnesium, and American submarines were systematically strangling the shipping lanes that brought raw materials to Japanese factories. Even if Japanese metallurgists could perfect the alloy composition, even if factories could tool up for production, the raw material supply chain simply couldn't support mass production of advanced aluminum alloys. Commander Nakajima's team calculated how much the armor protection and self-sealing tanks would degrade zero performance if added. The results were sobering. Adding 400 pounds of armor would increase wing loading by approximately 8%. Maximum speed would drop by at least 15 miles per hour. Climb rate would decrease by perhaps 400 feet per minute. Range would be reduced by over 200 miles. The turning radius would increase noticeably. The self-sealing fuel tanks presented both technical and industrial obstacles. Japanese engineers understood the principle perfectly. Multiple layers of rubber compounds, some natural and some synthetic, would line the fuel tanks. When punctured, the fuel would cause these compounds to swell and seal the hole within seconds. The British had developed this technology before the war. The Americans had refined it and deployed it universally across their combat aircraft fleet by 1941. But Japanese industry in 1943 lacked the synthetic rubber production capacity to manufacture these tanks in necessary quantities. Natural rubber supplies had been relatively plentiful in the early war years, when Japan controlled rubber-producing regions in Southeast Asia. But synthetic rubber production remained primitive and inadequate. The chemical plants and petroleum refineries needed to produce synthetic rubber compounds were the same facilities needed to produce aviation gasoline, explosives, and countless other war materials. Everything competed for the same, limited industrial capacity. Engineer Jiro Horikoshi, the original designer of the Zero, was consulted about possible solutions. His response reflected the impossible situation Japanese aviation faced. "We designed the Zero for a specific set of requirements in a specific industrial context," he explained to the Technical Evaluation Committee. Speed, range, and maneuverability were paramount. Protection was deliberately sacrificed to achieve those goals within the constraints of available engines and materials. Now the situation has changed. The enemy has more powerful engines, better materials, and superior production capacity. We cannot simply add what we deleted. The entire aircraft would need to be redesigned from the ground up. He continued with an assessment that struck at the heart of Japan's strategic dilemma. Even if we designed a new fighter today that matched the Hellcat's capabilities, it would take 18 months to reach production. By that time, the Americans will then have developed something even better. We are not competing against their current fighters. We are competing against their entire industrial and technological system, which is improving continuously and producing aircraft in quantities we cannot hope to match. The engine situation exemplified the technological gap. The Pratt & Whitney R2800 represented the culmination of decades of American radial engine development. The company had invested millions of dollars in research, employed thousands of engineers, operated advanced testing facilities, and benefited from the world's most sophisticated petroleum industry, providing high-octane aviation gasoline. The result was an engine that produced 2,000 horsepower reliably and could be manufactured in massive quantities. Japan's most powerful aircraft engine in production, the Mitsubishi Kinsei, produced approximately 1,300 horsepower. The Nakajima Hinomaru, still experiencing development problems, was designed for 1800 horsepower, but rarely achieved that in service conditions. Even if Japanese engineers could design an engine matching the R2800's output, manufacturing it in quantity would require machine tools, materials, and skilled labor that simply didn't exist in sufficient quantities. The situation with aviation gasoline proved equally frustrating. The Hellcat's engine used 100-octane fuel as standard, with 115 octane available for emergency power settings. This high-octane fuel allowed higher compression ratios and supercharger boost pressures, extracting maximum power from each cylinder. Japanese aviation gasoline averaged 92 octane, occasionally reaching 95 octane for special operations. The petroleum refining capacity and chemical processes needed to produce high-octane fuel consistently were beyond Japanese industrial capability in 1943, and the situation would only deteriorate as the war continued. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Test flights continued through late July and into August of 1943. Different pilots flew the Hellcat under various conditions to build a comprehensive understanding of its capabilities and limitations. Every flight confirmed the initial assessments. The Hellcat represented a fundamental shift in the air war, a weapon system optimized for the brutal realities of combat over the vast Pacific. Lieutenant Commander Shigeru Itaya, who had led the first wave of fighters at Pearl Harbor, flew the Hellcat in mock combat against multiple Zeros simultaneously. Even outnumbered 3-1, he could engage and disengage at will using superior speed and climb rate. The Zero pilots, despite being experienced combat veterans who understood energy fighting principles, couldn't force the engagement. Itaya could choose when to fight, where to fight, and when to escape. The initiative belonged entirely to the Hellcat pilot. His report emphasized the psychological impact this would have on Japanese pilots. Our pilots have been taught that superior skill and fighting spirit can overcome material disadvantages. Against the Wildcat, this was often true. A skilled Zero pilot could force the Wildcat into slow-speed turning combat and achieve victory. Against the Hellcat, this is no longer possible. No amount of skill or spirit can overcome the performance gap. The American pilot holds all the advantages and can refuse combat whenever the situation isn't favorable. The armament comparison proved equally discouraging when tested in detail. The evaluation team set up target panels representing typical aircraft structure at various ranges. The Hellcat's 650 caliber machine guns were test-fired at these targets to document their destructive effect. At 400 yards, a 1-second burst, approximately 60 rounds total, completely destroyed a panel representing Zero structure. The heavy projectiles punched through the thin aluminum skin, shattered internal structure, and would certainly have ignited any fuel tanks in their path. The Zero's armament was tested against similar panels for comparison. The 7.7mm machine guns proved nearly useless against any armored structure. They could damage thin skin and injure unprotected personnel, but they couldn't reliably disable protected enemies. The 20mm cannon were more effective, but the slow rate of fire and limited ammunition meant that pilots had perhaps 3 or 4 firing opportunities before ammunition exhaustion. Missing with any of those limited bursts meant running out of effective armament while the enemy still had thousands of rounds remaining. Japanese ordnance officers calculated ammunition expenditure rates in typical combat engagements. A Hellcat pilot could fire multiple bursts totaling 5 or 6 seconds and still have over half his ammunition remaining. A Zero pilot who fired all his cannon ammunition in 3 bursts of 4 seconds each would be left with only the nearly useless rifle-caliber machine guns. In extended combat, where multiple engagements occurred during a single mission, the Hellcat's ammunition capacity provided an overwhelming advantage. The captured Hellcat's instruments and equipment revealed other American advantages that seemed almost impossible to counter. The gun sight was a simple reflector design, but it was well designed and precisely calibrated. More importantly, it was robust and required minimal maintenance. The radio equipment, though incompatible with Japanese systems, showed quality construction that could withstand combat conditions. The generators and electrical systems were overbuilt to American standards, providing reliable power for all aircraft systems. Japanese aircraft electrical systems were consistently problematic. Generators failed, frequently. Wiring insulation deteriorated under tropical conditions. Radio equipment was temperamental and often failed at critical moments. The contrast reflected broader differences in industrial standards and quality control. American equipment was designed with generous safety margins and redundancy. Japanese equipment was designed to minimum specifications to save weight and materials, then manufactured with variable quality control that made reliability unpredictable. By September of 1943, the evaluation program had generated thousands of pages of technical reports, performance data, and tactical assessments. All of it pointed to the same conclusion. The F6F Hellcat represented a generational leap in fighter capability that Japan could not match with existing aircraft or industrial capacity. The question facing Japanese naval aviation leadership was stark and simple. What could be done? Several proposals emerged from various quarters. Some officers advocated for crash programs to develop new fighters that could match the Hellcat's capabilities. The Mitsubishi A-7M Reppu was already under development with this goal in mind, designed to carry armor protection, self-sealing tanks, and heavy armament, while maintaining performance through a more powerful engine. But the Reppu wouldn't reach production until 1945 at the earliest, and even then, production numbers would be limited by industrial constraints. Others argued for modifications to existing Zero variants to add minimal armor protection and improve armament. The A6M5 model incorporated some of these changes, adding small amounts of pilot armor and replacing the 20mm cannon with improved versions that carried more ammunition. But these incremental improvements couldn't close the fundamental performance gap. A slightly improved Zero was still a Zero, and it was still outclassed by the Hellcat in nearly every measurable category. Some advocated for tactical changes that might offset American material advantages. Emphasize surprise attacks, where the Zero's limitations mattered less. Avoid extended combat, where the Hellcat's superior sustained performance dominated. Use numerical superiority when possible to overwhelm individual American fighters. Fight at lower altitudes where the performance gap was smaller. These tactical adaptations would become standard Japanese practice, but they amounted to managing inevitable defeat rather than achieving victory. The most pessimistic officers, reviewing all the data and understanding Japan's deteriorating industrial position, concluded that air superiority over the Pacific was already lost. The Hellcat was just beginning to reach combat squadrons in significant numbers in mid-1943. By 1944, it would be everywhere, equipping every American carrier fighter squadron. Behind it, in the development pipeline, were even more capable fighters like the F-4U Corsair and the F-8F Bearcat. Japanese industry couldn't match current American capability, much less keep pace with continuous American improvements. Admiral Isoroku Yamamoto, who had reluctantly planned the Pearl Harbor attack while warning his superiors that Japan could only hope for early victories before American industrial power overwhelmed them, received the full reports on the captured Hellcat in late September 1943. His response was characteristically prescient, but tragically too late to change anything. This confirms what I have been saying since before the war began. We cannot win a prolonged conflict with America. Their industrial capacity and technological sophistication exceed ours by too great a margin. Every month, the war continues. That gap widens further. The Hellcat is merely proof of what I already knew. Yamamoto had been killed in April 1943, ambushed by American P-38 fighters that intercepted his transport aircraft over Bougainville. His death was itself a Preußer, demonstration of American capability. American codebreakers had read Japanese encrypted messages revealing his travel plans. American fighters had flown a long-range interception mission that Japanese fighters couldn't have duplicated. American gunnery had shot down his aircraft despite Zero escorts. The institutional knowledge, technical capability, and operational effectiveness that enabled that mission were the same factors that produced the Hellcat. The comparison between how Japan and America developed new fighter aircraft illuminated the fundamental differences in industrial approach and national capability. The Hellcat had been designed in response to specific combat lessons learned during 1942. Grumman engineers had interviewed combat pilots returning from the Pacific. They had studied gun camera footage showing where bullets hit enemy aircraft. They had examined battle-damaged Wildcats to understand what kind of protection pilots needed. They had analyzed combat reports to determine what performance characteristics mattered most in actual engagements. The design incorporated all these lessons: heavy armament to ensure kills with short bursts, armor protection focused on areas most likely to be hit in combat, self-sealing tanks because fuel fires killed more pilots than direct combat wounds, a powerful engine to enable superior speed and climb rate, robust structure to survive combat damage and carrier operations, simple systems that could be maintained by mechanics with basic training using common tools. Then Grumman had built the aircraft using industrial capacity that dwarfed anything available in Japan. The production lines employed standardized parts, precision tooling, and quality control procedures that ensured every Hellcat met specifications. Thousands of subcontractors provided components. The final assembly lines operated with efficiency that Japanese factories couldn't approach. By the end of the war, Grumman would produce over 12,000 Hellcats. Japanese production of all fighter types combined, from all manufacturers, would barely exceed that number. The American training pipeline ensured a steady flow of well-trained pilots to fly these aircraft. Flight schools throughout the United States churned out hundreds of new pilots monthly. Each received extensive training in modern fighters before deployment to combat zones. They arrived in the Pacific with dozens of hours in type, familiar with their aircraft's capabilities and limitations. Many had flown against experienced instructor pilots who taught them energy fighting tactics optimized for the Hellcat's strengths. Japanese pilot training, in contrast, was collapsing by mid-1943. The intensive, lengthy training programs that had produced the superbly skilled pilots of 1941 and early 1942 couldn't be sustained. Fuel shortages limited flight training hours. Experienced instructors were desperately needed in combat units and couldn't be spared for training duty. Losses among veteran pilots were mounting faster than experienced replacements could be trained. The quality of new pilots arriving in combat units declined steadily throughout 1943 and would deteriorate catastrophically in 1944. Combat results reflected the changing balance of capability. During the first half of 1943, when Hellcats were just beginning to deploy in small numbers, American fighter units began achieving increasingly favorable kill ratios against Japanese aircraft. By the second half of 1943, as Hellcat numbers increased, the kill ratios shifted dramatically in America's favor. By early 1944, when Hellcats equipped most American carrier fighter squadrons, Japanese losses became unsustainable. The Battle of the Philippine Sea, in June 1944, remembered by American pilots as the Great Marianas Turkey Shoot, demonstrated the complete reversal of fortunes since Pearl Harbor. American fighters, predominantly Hellcats, destroyed approximately 400 Japanese aircraft over 2 days of combat, while losing only about 30 American planes. The kill ratio exceeded 12-1. Japanese carrier air power, which had dominated the Pacific in 1942, was effectively destroyed as a coherent fighting force. Japanese pilots who survived these engagements consistently reported the same experiences. Hellcats appeared in numbers that seemed impossible. They attacked from superior altitude with superior speed. They used disciplined tactics that prevented Japanese fighters from exploiting their superior low-speed maneuverability. When Japanese pilots tried to turn with American fighters, the Americans simply extended away using superior speed. When Japanese pilots tried to escape, the Americans pursued using superior climb rate and diving speed. There was no escape, no successful tactic, no advantage to exploit. One captured Japanese pilot, interrogated after the Philippine Sea battle, provided testimony that confirmed everything the technical evaluation of the captured Hellcat had predicted. We were told our spirit and skill would overcome their material advantages, but there are limits to what spirit can achieve. When their fighters are faster, climb better, carry more ammunition, and can absorb damage that would destroy our aircraft, what is spirit worth? We die just as quickly whether our spirit is strong or weak. The industrial comparison became even more stark when examining production numbers in detail. In calendar year 1943, Grumman produced approximately 2,500 Hellcats. In the same year, all Japanese manufacturers combined produced approximately 7,500 fighters of all types, including Zeros, Oscars, Tojos, and other designs. But American production included thousands of other fighter types beyond the Hellcat: P-38, Lightnings, P-47 Thunderbolts, P-51 Mustangs, F-4U Corsairs, and continued Wildcat production for escort carriers. Total American fighter production in 1943 exceeded 20,000 aircraft. The disparity would only widen in 1944. Japanese aircraft production would peak at approximately 28,000 aircraft of all types, including bombers, trainers, and transports, not just fighters. American aircraft production in 1944 would exceed 96,000 aircraft. The numbers were so lopsided that they seemed almost impossible to believe, but they reflected the fundamental difference in industrial capacity between the two nations. Japanese industry was operating at maximum capacity, straining under resource shortages, labor shortages, and the effects of American submarine warfare that was strangling imports of raw materials. Every month brought new shortages. Aluminum production couldn't meet demand. Engine production lagged behind. Airframe production. Electronics and instruments were increasingly scarce. Quality control deteriorated as experienced workers were conscripted for military service and replaced with untrained labor. American industry, in contrast, was operating at perhaps 70% of theoretical maximum capacity and could expand further if needed. Raw materials were abundant. Skilled labor was available. The machine tool base was the most advanced in the world. Research and development continued unabated, producing continuous improvements. New aircraft types entered production alongside existing types. The entire industrial system was optimized for mass production of reliable, effective weapons. The captured Hellcat at Yokosuka continued to fly occasional test missions through late 1943 and into early 1944. Each flight provided more data, more understanding, more confirmation of American superiority. Japanese test pilots became increasingly proficient in the Hellcat, learning its capabilities intimately. Some expressed dark humor that they had become better Hellcat pilots than Zero pilots, that they understood the enemy's fighter more thoroughly than their own. In March 1944, the captured Hellcat's test program ended. The aircraft had accumulated over 150 hours of flight time in Japanese hands. Every system had been documented. Every capability had been explored. Every tactical implication had been analyzed. The conclusions were definitive and unchangeable. The F6F Hellcat represented American technological and industrial superiority, translated into combat capability. Japan had no answer, no counter, no way to achieve even parity, much less superiority. The aircraft was quietly destroyed to prevent it from being recaptured by advancing American forces. Engineers removed key components for preservation as examples of American manufacturing techniques. The engine was partially disassembled, and sections were sent to various research facilities for continued study. The armor plates were saved as examples of properly heat-treated steel. Some instruments and electrical components were preserved as reference standards. The airframe itself was scrapped, cut into pieces that were melted down to recover the aluminum for use in Japanese aircraft production. Lieutenant Commander Genda survived the war and later became a senior officer in Japan's post-war air self-defense force. In interviews decades after the war, he reflected on the captured Hellcat evaluation with the perspective of time and experience. Flying that aircraft showed me that we had already lost the war by mid-1943. The Hellcat represented not just a superior fighter, but a superior industrial system, a superior approach to warfare, and a superior understanding of what modern combat required. We were fighting yesterday's war with yesterday's philosophy. The Americans were fighting tomorrow's war with weapons designed for the reality we faced, not the war we wished we were fighting. Saburo Sakai, who survived the war as one of Japan's highest-scoring aces, despite being severely wounded and partially blinded, made similar observations in his autobiography published years later. The Hellcat was the weapon that destroyed Japanese naval aviation, not because any single Hellcat was invincible, but because there were so many of them, flown by increasingly well-trained pilots, supported by an industrial system that could replace losses faster than we could inflict them. I shot down several Hellcats during the war, but for every one I destroyed, 3 more appeared. We could win individual battles, but never the war. The technical reports generated by the Hellcat evaluation program were distributed to Japanese fighter units throughout the Pacific, with tactical recommendations for combat. Avoid extended engagements where the enemy can exploit superior speed and climb rate. Emphasize surprise attacks, where the enemy cannot react using superior performance. Break off combat before ammunition is exhausted. Conserve aircraft and pilots for critical moments, rather than accepting attritional combat that favors the enemy's superior numbers. These tactical guidelines acknowledged reality. Japanese fighters couldn't win sustained air superiority battles against American fighters, particularly Hellcats. The best Japanese pilots could hope for was survival through careful tactics and judicious combat selection. Even achieving favorable loss ratios became increasingly difficult as American pilot quality improved and American aircraft numbers proliferated. By late 1944, Zero pilots faced a combat environment where survival itself was the primary objective. American fighters were everywhere, in overwhelming numbers, flown by adequately trained pilots, employing sound tactics that negated Japanese advantages. The psychological impact on Japanese pilots was devastating. They flew obsolete aircraft against technologically superior enemies, who outnumbered them drastically and could replace losses while Japanese losses were increasingly irreplaceable. The kamikaze attacks that began in October 1944 represented, among other things, an acknowledgement that Japanese aircraft and pilots could no longer compete in conventional combat. Converting aircraft into guided missiles, accepting certain death to achieve damage, was a tactic of desperation born from the impossibility of achieving conventional victory. The Zero, designed as an air superiority fighter meant to dominate enemy fighters in combat, was reduced to a one-way weapon for suicide attacks. The final irony was that even in kamikaze attacks, the Zero's lightweight structure and lack of protective features became liabilities rather than advantages. American fighters could more easily shoot down incoming kamikazes because the thin skin offered no resistance to defensive fire. American shipboard. Anti-aircraft fire could destroy approaching kamikazes with hits that would barely damage more robustly built aircraft. The very features that made the Zero legendary in 1941 made it vulnerable in 1944 and 45. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The captured Hellcat that Japanese test pilots flew during those months in 1943 revealed a truth that some Japanese officers had suspected but couldn't prove until they had the physical evidence in their hands. The United States possessed industrial, technological, and organizational capabilities that Japan could never match. The Hellcat was simply one manifestation of that superiority, but it was a manifestation that destroyed Japanese naval aviation as an effective fighting force. Every advantage the Zero had exploited in 1941 had been systematically countered. American designers had accepted weight penalties for protection and firepower, then overcome those penalties with overwhelming engine power. American industry had produced these sophisticated aircraft in quantities that Japanese industry couldn't approach. American training pipelines had produced adequate pilots in numbers that Japanese training systems couldn't match. The entire American system, from design philosophy through industrial production to operational employment, was optimized for the kind of total war that would determine the Pacific conflict's outcome. The Japanese test pilots who flew the captured Hellcat during those evaluation flights saw the future with clarity. That future held inevitable defeat. The captured aircraft had revealed that Japanese hopes for victory through superior skill, fighting spirit, and tactical innovation were illusions. Material superiority, properly employed, would determine the war's outcome. The Americans possessed that material superiority, would employ it effectively, and would ultimately prevail. The morning Lieutenant Commander Genda first flew the Hellcat, taking off from Yokosuka on that clear July day in 1943. He carried with him the accumulated hopes and assumptions of Japanese naval aviation. When he landed 40 minutes later, those hopes had been shattered by direct personal experience. The radio message he would later review, the assessment that F6F outperforms 0 in all aspects, was not just a technical evaluation. It was an epitaph for Japanese air power in the Pacific War, written by those who understood, too late, that the war had already been lost before they had fully realized what they faced.